Hey there, in this video we are reviewing the use of arrays in a C++ program. So this review is covering chapter 7 of the Gaddis C++ book. Now, in the last video we were reviewing chapter 6 on functions, and the point of that is as you deal with larger programs with lots and lots of code, how do you handle that? Well, we separate the code out into separate slices called functions. The point here in chapter 7 is what happens when your programs are using lots more data, using hundreds or thousands or billions of variables. And so arrays are the most basic way that any programming language handles lots and lots of data. So you'll need this in larger programs, and you'll probably need this in every assignment all semester long in our Programming 2 course at CUNY Kingsborough. Okay, so basic idea of an array for review. So an array is a sequence of some data type. It's a whole bunch of data. That's what it is, one after the other in memory. Now, conceptually, what we would have liked to have done is we would have liked to have taken the idea of subscripted variables in math writing, right? Hopefully you're familiar with that. X subscript 0, or X sub 0 for short, right? X sub 1, X sub 2. So if you're working on math that's complicated enough that you've got more variables than letters in the alphabet, you start tagging them with a little number there called the subscript, and now you have as many variables as you want, right? Having with that number index in there, you can go x1, x2, x3, x 1,000, x a million if you want to. Great. So we are basically trying to replicate that. Obviously, you can't type subscripts on the keyboard, so we use the square brackets instead. But that's totally what that's trying to indicate. It's supposed to be a subscript. I'll probably actually call it a subscript, but quite a few times talking about it. So an array holds multiple values of the same type, right? Your array has to be all integers, or it can be all floats. You can't mix and match some of each. There can be any number of items up to memory. So it is very easy to make an array that has 100 things, or 1,000 things, or 1,000,000 things, assuming that you have enough free memory to do that. The values are stored in adjacent memory locations. So you do need to have one single contiguous connected free block of memory to make a big array. There can't be one piece here and one piece there and one piece in another place in the memory system. Now, later in this course, we will see different strategies for storing lots of data that actually do separate the data out in random places in memory. But an array is very, very simple and very basic. It's just like one long chunk in memory all together. And then once you do that, individual elements are identified by an integer index, and it is zero-based, remember. So here's a little example of an array in memory that has 5 things, right? It's a size 5 array. And the first index is 0, and the last index is going to be 4, right? Going to be 1 less than the size of the array. I'm sure you know that for beginning programmers, it's very common to get confused about that and to accidentally try to access a number 5, which is not in the array. And obviously that's an error that's so common, there's a name to it. We call it an off by 1 error. If that's ever confusing, you can kind of think of the index as it's the distance from the start, right? That's what it's telling you. So obviously the very first thing, that's distance 0 from the start. That is the start, right? And the next one down the line, which is actually the second thing, well, that's distance 1 from the start. So that's sort of what the index is telling you. Okay, you want to make an array. How do you do it? You're going to write something like this, right? That's an array declaration. Here's the type of the array. Here's a good name for it, right? And then square brackets, here's the size of the array. So arrays are indicated by square brackets. Would have loved to have used subscript notation, but this is how we do that in programming on the keyboard. And inside the brackets, there's the size of the array that you need. So every single element is all that same type, of course. That size has got to be an integer above 0. Can't use a floating point for the size. Can't use a negative. None of that would make any sense. Oftentimes, the size is going to be given by a named constant. So for example, before your array declaration, you might have const int size equals 100 if that's the size of your array that you need. You might even give it a better name than that. You might say number of students, right? Or you might say height of building, if that's what you have there. And the constant will be useful because you're going to need that number in later places. You're probably going to need it in a for loop. You're going to need to pass it as a parameter into functions. So again, having a named constant will be very easy for people to read and understand and change rather than having a number glued in the code in a dozen different places. So that's a good practice. Now here's a little detail at the end that sometimes I see beginning programmers get in trouble with, and I totally understand why. In standard C, C++ that's been standardized by an international committee, the size must be a constant, right? And that would include a literal, like if you actually wrote the number 100 there. But it must be a constant, it cannot be a variable. Now the problem is that some compilers break that rule and allow you to put a variable in the brackets in the array declaration. It's called a variable length array. The problem is, since that's technically against the rules of C++, if you take that code and take it to another compiler, it won't compile because not all compilers permit that. The other thing is it's been found to be a memory and security danger. For example, the code for the Linux operating system used to allow variable length arrays, and a couple of years ago they did a big effort to get rid of all of them because it was a security problem. So I highly recommend not using variable length arrays. And what I do on my compiler settings, I go in and I set the pedantic switch to actually enforce ISO, the International Standards Organization, version of C++, so I don't get into this trouble. The thing that I see beginning students do is they'll have a program that says that prompts the user, how many students do you have? Syn in that number to a variable and then try to declare an array of that size using the variable for the size. Again, technically not allowed under standard C++, and it's a security risk. So do not do that. Always use a constant for your array size. Now, once you do that, now you can start accessing things in the array like there are a bunch of separate variables. Okay, you just write down the name of the array and then in brackets the number, or here you can use a variable, and obviously we commonly do that with for loops, of course. That's a really nice thing about arrays is you can use a variable when you're accessing the elements, of course. So elements are accessed by brackets after the array name with an integer index. And they just act like a bunch of separate variables, right? You can assign them now, you can use them in syn statements, you can pass them into functions, whatever you want. Here's a little bit of technical information that you probably didn't get in Programming 1. What is really happening when you write down an array access statement like we're looking at here? Now, number one, the name of the array itself is technically holding the address in the memory system of where it starts, right? The name of the array is actually holding the address of where, like what byte in the memory system where the block of memory starts. That might seem like a really technical little fine point, but that'll be important in about 5 slides if I recall correctly. So when you write down name bracket index, what the computer actually does is it takes the address, right, of where the array starts, it takes the index and just adds them together. It just does a plus job on them. And that's the address of where your variable is, right? And that actually explains a couple things, because that explains why array indexing starts at 0. Right? If you do name bracket 0, it takes the address of the start plus 0. Well, that's the address of the start, of course. That's totally where the first variable is, right? And if you do name bracket 1, it is name plus 1, and that's the next one down the line. That's totally why arrays are indexed starting with 0, because it's just doing an addition, really, on the memory addresses. This is the kind of thing we talk more about in Programming 2 here. And once you do that, it basically just works like a variable. Great. Nice. Okay, here are some common algorithms, right? Some very common jobs that we do with arrays that you should be familiar with. So we'll review a little bit. I think many of the assignments that I give in Programming 2, they frequently have to use these algorithms again and again and again, almost on a weekly basis. So hopefully you're familiar with these and you can hammer one of these out when you need to. Finding the sum of an array, right? Getting the total of all the numbers in the entire array. So we process arrays with for loops, right? You know how big it is to begin with. You've got the size already, and for loops are the best loop to use when you know the counter in advance. So they work really nicely together. So here's a little slice of code getting the sum of an array. right? What we're doing here is we're using an accumulator, a variable that's getting stuff added into it. And that was first presented back in chapter 5 to add together all the array elements. So on line 18 in this little slice, you have this accumulator variable. It's called total. You have to initialize it to 0, just like a cash register starting out. Right? Common mistake is that students forget to do that. And then you've got uninitialized data and you've got random garbage in it, like we talked about, I think, 2 videos back. And then the total isn't going to be right at the end either. And then you have a for loop that's counting from 0 to less than the size, right? Because the size is, again, if a 5-element array doesn't actually have an array number 5, right? It would stop at 4. And then as you step through the array there, array bracket 0 gets added in a total, and array bracket 1 gets added in a total, and array bracket 2 gets added in a total, all of them. And then after that for loop is done, total does actually hold the sum of all the things in the array. And you can return it from a function, you can print it out, you can use it in a calculation, whatever you needed that total for. And obviously, if you're ever asked to find the average of an array, you need to do this first, and then just divide the total by the size. And you'll have the array, the average of the array, obviously. What else? Finding the maximum of an array, right? Finding the biggest thing in an array is important. And you can see that this is the strategy that our textbook uses for that, at least. So you're going to have this variable that's called highest here that is basically holding the highest thing you've seen so far as you search through the array from start to finish. So on line 26, presumably this is an integer array. They're declaring a new variable called highest, and they're initializing it to the very first thing in the array, which of course is array index 0. Then your for loop is going to go from 1 to less than size. We've already looked at index 0. You don't have to do it again. So here it goes from 1 to less than size. And as you inspect every single thing in the array, you make the decision if this thing, if array bracket, the current count, 1 or 2 or 3 or 4, whatever, is bigger than what you've seen before, right? Bigger than what you've recorded as highest before, then you better reset highest to what you're looking at, because that's the biggest thing so far, right? So hopefully that makes sense. And then once that loop is done, highest, that variable will definitely have the biggest thing in the array. And you can return it or print it or use it in a calculation, whatever you need. So that variable, right, that's holding the highest thing we've seen so far, it shows up before the loop where it's initialized to the first element. Inside the loop, you're checking to see if the next thing you're looking at is even higher than what came before it. And then after the loop, that variable does actually hold the maximum element. Now you might also ask, how do I find the smallest thing in an array, the minimum? And basically, sometimes I ask this as a quiz question in class. It's this exact same code. Nothing needs to change except the direction of the relation on line 28 in the if statement there. You just switch that greater than to lesser than, and this exact same slice of code spits out the lowest thing. Now I would also then change the name of my variable from highest to lowest under my principle of a variable should do what it says and say what it does. If it's the lowest thing, call it lowest. All right, now here, for all the features in C++, there's usually some risk involved that you need to be aware of. C++ is so powerful and therefore also very dangerous. So, with variables, the primary danger is to leave them uninitialized, and you get random garbage. With loops, the primary risk is to have an infinite loop if it gets bungled. And here's the most dangerous thing of all, actually, is buffer overflows. So a buffer overflow, and buffer basically means array here. A buffer overflow is accidentally writing data past the end of an array and therefore overwriting the adjacent memory. So you probably got some array, but then there's other variables stored in memory after that. So if you accidentally run off the end of the array, you actually are corrupting and overwriting and erasing other variables that are probably important to your program. So you see, the reason this is an issue is because C and C++ does not record or check array limits automatically. Now, some other programming languages do that. Like Java has what I would call a memory cop, that's always checking in every single write. Is this actually in the array? Is this right? Is this memory location actually in the array? And if it's not, it stops that from happening. So it's safer in that sense. But it's also a little bit slower because the CPU is getting used up a little bit to do this traffic cop job. The priorities for C++ were set up differently. The priority for C++ is full speed ahead, right? We want maximum efficiency, maximum speed if we need to control a car or a rocket ship or a link to somebody's brain, right? We want full capacity happening all the time. But as a result, that's dangerous. It is possible to go past the end of an array and possibly corrupt the memory. And I'm sure you could have an hour-long debate about which of those philosophies is better. And I'm sure someone could come in and say, the speed that Java takes to do the traffic cop job is so negligible, you'll never notice the difference. I'm sure someone could say that. But that's not how C++ was set up, and that's not the priority for it. So as a result, if you're working in C++, you don't have any safety bumper. You, the programmer, have to be careful to keep track of the size of your arrays, for example, with a named constant, right? Use the named constant so you're not guessing at the size of your array. That's very smart, like we said. Otherwise, the access may go past the end and overwrite other variables, other data in memory, and then practically anything can happen at that point. And it's going to be very confusing and very mysterious. The program could crash. There could be a memory leak that your memory is being lost inexplicably. There can be hacking vulnerabilities. There can just be crazy, crazy bugs that are hard to fix. So for me, if I have a program that just looks like it goes nuts and crazy stuff gets printed to the screen and sometimes it crashes and sometimes it doesn't and it pauses and it restarts and there's garbage on the screen, my first guess is probably there's a buffer overflow. So I go hunting for my arrays and checking the loops and doing a detective job that probably there's a buffer overflow somewhere in the system that's causing just insane, crazy, maniacal behavior. I will also say that to a large extent, if anytime you see a news story about hacking, right, or security problems, the majority of the time it's because of a buffer overflow. And that is one of the more embarrassing things, frankly, about C++. It's an older language. That wasn't the priority. But most of the hacking issues in the world are, frankly, because somewhere there's a buffer overflow that someone discovered and took advantage of. All right, some other things. You should be able to make a partially filled array. Commonly, an array will only need to store some subset of its total size. For example, if the program starts up and you don't know how many data points you'll need to store when the program starts up, just give it some large size, give it some arbitrarily large size, more than you need really. And then as data gets saved there, you can use a separate counter variable to keep track of how many things you've saved in the array so far. Now keep in mind that that variable is different from the constant for the full size. So I might have a constant that says my array is size 100, right? That's the full size. And then I'll have a separate variable to say, currently I've stored in from the user 1, 2, 3, 4, 5 things, right? So the number of things that have been put into it is just 5 so far. And that is called a partially filled array. Now, if you think about it, that's sort of the flip side to the issue that you're not allowed to have variable length arrays in official C++, right? So granted that you can't ask the user, how many things do you have, and then make an array of that size so far in the class, right? The beginning solution to that is just an arbitrarily large array and then count how many things you're storing there so far. That's called a partially filled array. There's a number of examples in the book in chapter 7, and you should know how to do that. Passing arrays into functions, right? As we said in the chapter 6 review, we are definitely going to modularize our programs all the time from now on. They're always going to be split into functions, and the only information the functions are ever going to use is the information being passed in from parameters. So if a function needs to access an array, you need to know how to do that. Here's what that looks like in C++. So your function prototype is going to look like, here's the return type, here's the name, here's the type of my array, square brackets that are empty. Not going to be anything in those square brackets, just saying this thing here is the name of an array. And then there's going to be a second parameter, right? There's going to be an integer that tells the function how big the array is. That's going to be indicating the size. So in some other languages, you would just have to pass in the array by itself. But in C++, you are going to have to separately pass in these two things, right? The array and the size. So definitely get it in your head and get in the habit of, I'm passing an array into a function, two parameters, right? The array and the size, which is obviously an integer. So then when you actually call the function, it just looks like this. Name the function, right? Just name the array. Don't need any square brackets at that point. Just name the array and then give it the size of the array, and the function will have access to it and know what to do with it. So you remember 5 slides back when I said, like, what is the name of an array all by itself? Because that's what you're seeing here. Just name of an array. No brackets, no number, nothing, right? What does that mean? So if you remember from a couple minutes ago, and here we are passing, arrays into a function as arguments. We needed to do that. Requires 2 parameters, like we say. Now remember, the array name doesn't actually hold data. It holds the address of where the array starts in memory. Has the address. So as you do that, think about what else is passing an address in from like the last video. Well, that's just like how pass by reference works, right? The whole point to pass by reference for parameters is you're really passing in the address of where the thing is. You're not making a copy of it. And so since the name of the array is actually the address, that's exactly what happens here automatically. So effectively, passing arrays into functions, they're always passed by reference. Great, okay? And that makes sense to me. Remember, the time that you would want to pass something in by reference is when it's really, really large. Because the normal thing, passed by value, would make a copy and you'd be wasting a whole lot of memory. So you don't want to do that with large data structures. And that's exactly the solution, is you pass in the address instead, you avoid making the copy, you avoid wasting a lot of memory, you avoid wasting time on the CPU actually making the copy, and then the function does have access to that whole array there, and it knows how big it is because of the size. Now think about the danger there, because the function can then go and change what's in the array, right? Because it does have full access to it. Maybe we'll look for solutions to that later on. But the point here is when you're passing an array into a function, there are going to be 2 parameters, the array and the size, and it's effectively passed in by reference, which is great because it's very fast and very efficient. Okay, don't forget about 2-dimensional arrays, right? You can make multi-dimensional arrays like this. Here's the return type, here's the name of the array. Now you have 2 square brackets indicating the 2 dimensions of the array. So 2-dimensional arrays provide a way to structure data kind of like a table, right? Columns and rows. So you can think of them like that, or you can think of it like XY locations in a Cartesian coordinate system. You can think of it like a mathematical matrix, right? It's the number of rows, again, the number of rows and number of columns, if you've seen any of linear algebra with matrices at all. So very, very useful for all those kinds of jobs. Technically, it's an array of arrays, right? I have an array of size 2. What's the type? Well, it's array of size 1 is technically the type. So what happens in memory is you have this first array, and then you have right after it, you have another one of those, and you have another one of those, and you have another one of those. And that's actually what's happening in the memory system, but you have this very convenient syntax in C++ that just takes care of all those different locations automatically. So once you've done that, you can access the entries by specifying both the row and the column. Right? You're going to write down name, bracket which row you're in, bracket what column you're in, and it works very nicely. Very convenient to process a 2-dimensional array using nested loops. So you have a for loop that's counting over the rows and an inner for loop that's counting over the columns. And again, for loops and arrays work really nicely together like that. In this case, 2-dimensional arrays and nested loops. I think we see that in at least a couple labs or exercises early in the course, I believe. Of course, you can have more dimensions then. You have 3 or 4 or 5 dimensions if you want. You will be using up a lot of memory very quickly. Honestly, I don't have to go more than 2 dimensions in my work very much at all, so you'll probably just see 2-dimensional arrays in this course. I think this here is the last slide for our review here today. You should know about type aliases, otherwise known as type defs, type definitions. So what a type def is a keyword in C++, same as C, which is short for type definition. And basically, you're just making a new name for an existing type, basically. So you say type def, here's an old type like int or float, and here's a new type that I want to refer to it by a new name, which is more expressive and more understandable for the job that I'm currently working on. So a type alias defines a new name for an existing data type. The point is that declarations using the new type name should be clearer or shorter in some way. So a little example, let's say I write down type def int timesheet, capital T, timesheet bracket 7. So what that's doing is it's defining a type, which is an array for holding hours worked daily. It's for a timesheet, okay? Now, that's the same as integer bracket 7, which is to say an array of integers size 7. But if I'm working on a program that needs to use data of this form a lot, I don't want to have to keep writing int bracket 7, int bracket 7, int array size 7, int array size 7 over and over again. I want to just write timesheet, right? Here's a block of data that represents a 7-day timesheet. And now I can just write timesheet for my declarations and my parameters and my return types if I want to, right? And so you don't need to, this isn't strictly necessary, but again, it's nice. We tend to find it better that our programs have expressive names that people can recognize very easily. And this shows up in a lot of the labs that come with the book at this point. That's really why I've got this slide here. Okay, so I think that's a pretty good review of Chapter 7. And if you're a student in my course at this point, optionally, I would point you to the Programming 1 lecture slides. That's CS 1200 at Kingsborough. So this is the end of our review component. Hopefully that's a reasonable 3-day refresher on the basics of control structures and data, functions and arrays. And starting the next video, there'll be presumably new material for our students. If you need to, you can go get the full lecture slides for my Programming 1 course, and you can review that on your own. Would be a good idea to start this course. And at this point, I ask that students do the first programming challenge in Programming 2 that's in Chapter 7. Now, technically, Chapter 7 was covered in the last semester. So this is totally an assignment you could have done 1 semester ago. And that is what I ask students to do to begin with. So in my course, look at the learning management system, see exactly what I'm asking for Programming Challenge Chapter 7, and that'll be the first programming grade that you get in the course. And then when we're together in a lab session, I would probably do Lab 7.3 as the first communal programming exercise together, kind of probably brush off some Rust a little bit and get back into programming. And that's a lab that is working with 2-dimensional arrays. So you get some information from the user, I think about like quarterly sales, and at the end on the screen in a nicely formatted table with nice columns and nice rows, using like the set width function and stuff like that, you're going to print out the data that was stored in the 2-dimensional array. So it's a pretty good initial lab. It's got separate modular functions, right? You've got a 2-dimensional array. You're passing the array into those various functions that do different jobs, and you're nicely formatting your output with IO manip functions and stuff like that. So if you have access to the lab code that comes with the Gaddis book and you want to try it on your own, freeze the video here and feel free to try it on your own. And that is a great opening exercise for second semester programming. Okay, so hopefully that was a good little review component. You kind of know if you need to fill in things that you're rusty on, you know where to get additional information. Obviously, the book is great. You should have that. My lecture slides that I've got on CUNY Academic Commons for both semesters is available in a link in the description on YouTube for what it's worth. And we come back next time, we'll be dealing with the new material for my students in Programming 2. We'll be starting in on Chapter 8 on searching and sorting arrays specifically. So that's why we wanted to review this. And boy, searching and sorting is so important in computer science. It's really fundamental to a lot of what computer science does and really lays the groundwork for the kinds of things we want to think about as advanced computer science people. So I'm personally really looking forward to getting into searching and sorting in Chapter 8 next time. So I'll see you then.